Swayam Prabha. Digital India. Educated India.
Good morning, everybody. So, myself, Dr. Arnab, I am currently an associate professor of this department, and I basically work in the area of little bit organometallic chemistry and catalysis. So, today I'll try to highlight some of the important sigma donor ligands in organometallic chemistry. So, I'll come back what I mean by sigma donor ligand and pi acceptor. You have some idea in organometallic chemistry, but specifically I'll cover few of the ligands which is very important in organometallic chemistries and a little bit focus on the catalysis, why they are important. Now, before going into details, these are the standard textbooks if you wish, and you can follow it. For example, first one is the Seaver Atkins, which is a very standard textbook, inorganic textbook for the PG as well as weak heater gator, and this B.D. Gupta and E.G. Elias, that is the basic organometallic chemistry book, which is very important for the organometallic chemistry because it covers a huge area of organometallic chemistry with so many new concepts which might not be so detailed in given in these books. So, before going into that the different ligand system, let us have a look in this matters why we need to study at all organometallic chemistry. So, this is a very fascinating word, organometallic chemistry. Whenever we take interview, everybody says that we want to do it in organometallic chemistry. Now, the question is, why is it important? So, let us have a look in the Nobel Prizes which were given to organometallic chemists. First, it started back in 1963, and this that time Nobel Prize was given to Ziegler and Natta for their pioneering invention in stereoregular polymers. So, starting from ethylene, and they could polymerize it. It's a stereoregular polymer, and you get the corresponding polyethylene. So, based on this titanium and aluminum based catalyst. Later on in Lipscomb in 1976, he got the Nobel Prize because of some boron structures and their chemical bonding. And it keeps on moving, as you see here in 1979, Brown and Utig for their contribution in the boron and phosphorus containing compounds. Later on, if you see in 2001, it is very well known reaction by surface oxidation, you might have heard about it, Knowles and Noyori, that is also asymmetric hydrogenation reaction, they are all given together. And later on, this is in 2005, Chauvin, Grafs and Sox are given the Nobel Prize for the development of metathesis reaction in organic synthesis. So, today I will try to cover a little bit about that. So, why it is important in organometallic and organic synthesis. And the latest one here, as you all know about the coupling reaction, which is a CC coupling reaction, palladium catalyzed CC coupling reaction, and for that they were given Nobel Prize in 2010, the Heck, Negesi and Suzuki. Okay. The Heck and Negesi, they are not no more here, but Suzuki is still. So, they are very important reaction in starting from organometallic chemistry, which is the basics here, but it can expand in organic synthesis, material chemistry, everywhere. So, therefore, they are very important to study. Now, one of the important aspect what you need to know about the organometallic chemistry, what is organometallic complexes. So, as you know, so this name suggests that organometallic. So, that name suggests complex. So, as the name suggests, there is organic and there is a metallic fragment, okay, but that is not all. If you have organic fragment and you have a metallic fragment, you cannot call this an organometallic compound. Now, the question is that then what type of compound you should call this an organometallic compound. So, first criteria what it says that it should have a metal carbon bonds, okay. So, if this is the one of the criteria which the basic criteria you can look at it, if you have a compound and it has a metal carbon bond, then definitely you can call it as a organometallic compound. So, for example, the well known ferrocene, okay, it has a metal carbon. So, the bonding between the metal and carbon, it can vary, it could be ionic, could be covalent and could be bonded to a particular atom, or it could be delocalized, all types of things are taken care. But some of the cases you also might have heard about it, that what is this compound? Wilkinson catalyst. Now, should we call this as a organometallic catalyst? No, no carbon bond, okay. But when you are talking about this compound, as such is not a, by definition is not a organometallic catalyst, okay. But just to clarify it, so it does not have to be, this compound does not have a metal carbon bond, but when it undergoes reaction here, so if you remember that first step is the dissociation of phosphine from the metal. So, it basically forms, there are two mechanisms, I am not going into detail, but you basically after hydrogenation also it may happen or before also it may happen. So, you have this species, right. So, this is after hydrogen addition. Now, there is a vacant coordination site where alkene binds, right. So, by this way what is happening there, there is a metal carbon bond is forming in the catalytic cycle. As such, this compound is not an organometallic catalyst or organometallic compound, but in the process of doing the hydrogenation, what this catalyst does, it just taken this hydrogen catalyst and you get the corresponding saturated species. That is the role of this catalyst. Now, in the process is basically generates some of the species which may contain the metal carbon bond. So, in that respect you may call this compound as a organometallic catalyst, because when you use the term catalyst, because it does a catalysis. So, this is the way you can think about it, okay. And now, this is the one of the, this is the first examples of organometallic compound, is a very well known species, what is called Geisen's species, but this is one of the species which is this synthesized in 1827, but the problem there, that time people did not know how to characterize this compound. Nowadays you are also the every day you are looking at different instrumental facility in our department itself, and you see almost everything is there. So, immediately if you synthesize a compound, go there and find it out what is the structure of that compound. The back like 200 years back there was nothing except the combustion method, which will give you some sort of idea about the carbon, hydrogen, nitrogen content. So, that was very difficult. As you see here, the real structure was known only was established in 1975. It took almost 150 years to understand the structure of that compound. So, later on today I will also go into a little bit of details of the structures, bonding of this type of alkene complexes, and as you see that other compound also there, nickel carbonyl, Grignard reagent, all are known in that. Not only that, if you see in nature also there are a lot of organometallic compounds present. For example, this is cobaltamine, vitamin B12, which has a metal carbon bond. So, if you just strictly go by that there should be a metal carbon bond, we can also call this compound as a metal carbon organometallic compound. Now, one more concept what you normally use in organometallic chemistry, the compound whatever is organometallic compound we are talking about, they should follow 18 electron rule, okay. So, this 18 electron rule, just briefly go through it. So, it is nothing but the number of electron metal has it, d electron to be specific, and the number of electrons that ligand contributes to it, then it should be total 18 electron. Now, the question is why 18 electron species are stable for organometallic compounds? Why specifically 18? Why not it should be 16? Some cases even though specific cases, square planet cases. So, why it is a specific number 16, 18 and mostly 18 organometallic compound, and then some cases 16. Why it is specifically this is an 18 electron species which is stable. So, for example, if you take the chromium CO6, you get 6 plus 2 into each carbon monoxide donates 2 electron because carbon monoxide has 2 electron here as a lone pair, and then 2 into 6. So, you have a total 18 electron. Okay. So, this is a stable species we can demand. Okay. And here also if you do it, then it is an total how many electrons? Do you know how to count there? Huh? Do you know or do you don't know how to count it? No. Yes. Some says yes. So, this is the iron, there are two methods. Okay. So, one is neutral atom method, one is oxidation state method. Whatever you wish you can use it, but the caution is you should not combine, because oxidation state method means you will consider as a Fe plus 2. So, then accordingly the electron count will be, it will be negatively charged ligand. Okay. So, then you will have here how many electron? 6, iron is 26, this is a 2 plus. So, it will be 6 plus 2 Cp ligand is that 2 into 6. So, 18 electrons. Now, just simply if you change this iron to cobalt, what is the electron count? Iron, then the cobalt. Okay. So, this one more electron extra, nothing else. If it is a cobalt, this is a cobaltocene. This is a ferrocene, when it is based on cobalt, it is a cobaltocene. So, this is also plus 2, then it is a 7 plus 2 into 6, this is a 19 electron species. Now, based on this our 18 electron rule, we can comment on the reactivity of this species. This is 18 electron species. Okay. So, therefore, it is a very stable species, no question about it, and then it is a 19 electron species. So, it has 1 electron extra. Now, if I ask you between this ferrocene and cobaltocene, which will be a better reducing agent? Reducing agent means which can reduce something. Reduction means that will be accepting electron, and whatever the reducing agent will be oxidized. The species want to reduce, that should accept electron, and the species you want to use as a reducing agent, it has to oxidize, it has to lose the electron. Now, if you see that electron count between 18 electron and 19 electron, which one will be better reducing agent? Cobaltocene. So, it is based on that, because it has a 1 electron extra. So, basically it wants to go for a plus, then it becomes an 18 electron species, which is a stable species. So, that is how the simple 18 electron count will also help you to understand the reactivity of this species. Okay. Now, other way, if you take this cobaltocene versus ferrocene, cobaltocenium versus ferrocenium. So, this is a 17 electron species. So, it wants to take one more electron to make it as a 18 electron species. So, that means it will work as a oxidizing agent, so that it can accept the electron to become an 18 electron species, but this will not do it because it is already 18 electron species. Compare relatively, if you see, ferrocenium will be better oxidizing agent, whereas cobaltocene will be better reducing agent. So, this is a simple calculation will help you to understand. Now, the question coming back to this, why this should be an 18 electron species to have a stable structure. So, now if you see that metal has 6 electron and carbonyl has 6 carbon monoxide. So, each giving the 6 into 2, 12. Now, if you go back, I do not know how much you know about the molecular orbital. So, so this is a just to give you an idea, you do not have to go into details about the molecular orbital. This is a metal orbital. this is a chromium. Okay. So, this chromium transition metal cases, you know that it is a octahedral species because it is a chromium CO6 you have taken, or any metal you take it is an octahedral system. So, if it is octahedral system, we know the d metal orbital splitting in octahedral, it just splits into T2G and Eg. So, that is what you know, that you have 1, 2, 3, 4, 5 and it splits into T2G and Eg. Okay. In tetrahedral it will be just reverse with the T2 and E. Okay. So, now you have 3 orbital here T2G and this is the 2. So, overall capacity of this is total capacity 6. Okay. So, you may have maximum we can have this, okay, this is 6, and you know this Eg orbital is slightly anti-bonding. Okay. So, you do not want to have a configuration where the electrons are in the anti-bonding. You want to have it everything in bonding, that is why it will be stable species. Now, if you look at it here, you have 3 orbitals which can accommodate 6 electrons. Now, if you look at here, so this is the molecular orbital of the particular species MCO6 species if you are given. So, in that case what happens that there are 6 carbonyl which is a ligand orbital. So, if you how to construct the molecular orbital, then you have to make the ligand group orbital and all those things, you have to, it's a little bit complicated, you do not have to look at it, but if you see that all these 12 electron which 6 carbonyl is donating, these are the orbital where it can accommodate 1, 2, 3, 4, 5, 6. So, 6 orbital there which is bonding and that can accommodate maximum 12 electron here, and then from the metal orbital which is T2G, that can accommodate total 6 electron, because whenever you go to the above to that, then you have a anti-bonding orbital. System does not want to populate the anti-bonding orbital, it only wants to have all the bonding orbital filled. If you have an unpaired electron here, it is not completely filled, so that means it will be, let us say 17 electron. So, then there will be one vacancy, the system is not a very stable system. But if all the bonding orbitals are filled with all the electrons are paired up, completely filled bonding orbitals, that will be the most stable species. So, overall what we see here, you have total here 6 plus 3 9 orbital bonding orbital which can accommodate maximum of 18 electron. So, that is the origin why 18 electron species, what you have learned that stable species. Okay. So, based on that understanding, you can also go to the corresponding 16 electron species which is specifically corresponding to the square planar complex, where one more orbital will not be accessible very high in energy. So, you will have in total 8 bonding orbital which you can accommodate total 16 layers. Okay, this is fine. So, now is it clear or I should repeat? It's clear. Okay. Now, so in organometallic chemistry, whatever till now we studied, mostly it concentrates on carbon monoxide ligands first. Then we will slowly move to the other ligand which is phosphine, and lastly we will go to the new set of ligand system which is called as a N-heterocyclic carbene. What are their features? Why people have come up with such a ligand system which replaces now all this PR3 which is a tertiary phosphine. What is the features which makes them so attractive? So, that is what we will try to see, and finally we will try to see how you can combine different compounds to activate small molecule. This is the overall aim of today's class. Now, if you see this carbon monoxide, what is the bond order of carbon monoxide? Bond order means how many bonds? 3. So, it is a C triple bond O, right. So, now do you know how to construct the molecular orbital to find out this a 3? You have any idea why it is 3, why not 2? If I say 2, what is wrong? You do not know, okay. Let me just quickly go through it. So, as a bond order is equal to number of anti-bonding electron minus number of bonding electrons, right? Bonding minus anti-bonding. So, bonding minus anti-bonding electrons divided by 2. So, in order to find out the bond order, you actually have to find out the number of bonding electrons, anti-bonding electrons, like that what we have seen here. So, if you want to find out the bond order, you have to go to the bonding and anti-bonding orbital, that you can only get when you have a molecular orbital picture of carbon monoxide. This is, so how to construct it? Carbon has a, what is the configuration? 1s, 2s2 and 2p2, 6, 2p2. Oxygen, right, this is the overall electron configuration, that is an atomic level. But when you are talking about carbon monoxide, then it is a molecular level. So, you cannot deal anymore with the carbon and oxygen, you have to go to the system where you have a both carbon and oxygen combined as a new orbital picture. So, in that case, if you look at carbon, let us say we put 1s, then 2s and this is 2p, right. This is not exactly paced according to the energy, just to show you. So, now 1s and then oxygen cases, let us say this is a carbon and oxygen cases, because oxygen is more electronegative than the carbon, the energy of the orbital will also be little bit lower because it is more electronegative. So, therefore, the energy is lower. So, let us say carbon here, this is there and this is like a 2p, 2s and this is a 2p, right. So, now if you see that this 1s orbital, the one of the criteria for the molecular orbital is that number of atomic orbital combining should generate the same number of molecular orbital. So, if you are thinking here this is 1 plus 2 plus 3, so this is 5 plus 5, so you should generate total 10 molecular orbital, as simple as that, and number of bonding orbital whatever you are generating, that should have a equal number of anti-bonding orbital. So, if you see there 1s orbital, then it can generate the 1 sigma, 1 is sigma star, okay, same. So, you have 1s orbital, you have 2 electron, this is a 2 electron, so it goes like this, 2 electron plus 2 electron, this goes like this. So, it is anyway does not contribute to the overall bond order because it is nullified, number of bonding electron minus anti-bonding electron is 0, okay. The same way when you go for, so, but one thing you will see that whenever this oxygen is lower in energy, so this bonding orbital is closer to the oxygen and this anti-bonding orbital which is higher in this is closer to carbon. So, same way if you see here, there will be 2 electron and 2 electron, this is also another sigma and this is a sigma star. So, overall it is also nullified, there are 2 electron and 2 electron on the anti-bonding orbital. Now, if you go for the 2p orbital, what are the 2p orbitals? Is a px, py and pz. So, this is nothing but this is along the x axis, y axis and z axis. Now, if you see that if you consider z axis as the bonding axis between carbon and oxygen. So, this pz orbital is along the z axis, right. So, this is a z axis and the if you are considering the bonding axis is as a z axis. So, the carbon and oxygen orbital 2pz orbital coming along the axis. Now, what is the difference between the sigma and pi bonding? Sigma bonding means when it is a face to face and then sidewise overlap is the pi bonding, that is the only difference. So, if you see here pz orbital, if you consider this is a z axis, then you have that. So, this is a plus and this is minus, plus and minus, that is it. So, if you take a pz orbital and here is a pz orbital, right. So, it is a face to face, so that it is a sigma type of bonding, okay. So, one will be sigma, but then if you think about the py which is perpendicular to that, right, z axis and y axis is perpendicular. So, in that case what will happen, this is a plus and plus, minus and minus. So, that will correspond to pi I, okay. So, between this 2p orbital which has px, py and pz, it has 3 orbitals, out of 3 one will go for a sigma bonding which is pz and px and py will go for a pi bonding. So, overall what we will see here, there will be 2 pi orbital and then there will be 1 sigma. Okay, this is a sigma orbital, and accordingly you will have the corresponding p and sigma star, pi star and sigma star. Now overall, how many electrons should be there? So there are 2 electrons, they nullified, and then 2p orbital. How many electrons you have for the oxygen? 4 electrons, and then from the carbon, so how many electrons you have? 2. Carbon has 2 and then oxygen has a 4. So total how many electrons you have? 6 electrons. So 1, 2, 3, 4, 5, 6. Right? So how many extra electron you have in the bonding? These are all bonding orbital, they are anti-bonding orbital. So overall you have 6 electrons in the anti-bonding in excess as compared to the anti-bonding. So the bond order will be 6 by 2 overall, right? So that's how we get the carbon and oxygen as a triple bond. Now to go into bit more detail, this is a sigma electron and this is centered on carbon, and that's what we see that in carbon monoxide binds to carbon, not from the oxygen, because here carbon lone pair, which is this is called as a HOMO. You know what is HOMO? HOMO is highest occupied molecular orbital. This is the highest occupied molecular orbital, whereas this one which is of pi star, and this is called as a LUMO, lowest unoccupied molecular orbital. These are the important molecular orbital, which is the frontier molecular orbital, HOMO and LUMO, involved in the bonding of carbon monoxide, what you have studied. Now if you see here now, carbon monoxide which is having bond order of 3, that is what we have calculated based on molecular orbital. Now in this case what we see, it has one lone pair of electron, okay. So this is, if we put it as sigma orbital, because that is what the sigma orbital here, which is a HOMO. So that has a lone pair of electron. Now it has also a pi star, next available orbital is pi star here, which is an anti-bonding orbital. So this is looking like anti-bonding, means there is no proper overlap. If you say overlap is face to face overlap, this is bonding, and opposite phase overlap is anti-bonding. So in that case you will be plus, this is minus, and this will be plus and minus. Okay. When you think about the metal, it may also have metal d orbital. What are the orbital? dxy, dyz, dz, and dx square minus y square, dz square. So this, if you think about again the z axis as a axis of overlap, then dz square will have. So there, this is, that's how this will form a sigma bonding scenario here, and obviously it has the other orbital which will again be pi type because of the position, so overlap position. So overall you will have a bonding situation where it will be donating back to the pi star. Pi star is an acceptor orbital, whereas this one is an donor orbital here. So that's why this carbon monoxide, we call it as sigma donor. It has a sigma orbital which is donating the electron, having two lone pair of electrons, sigma donor, and as well as pi acceptor, because it has a pi star orbital of the carbon monoxide. Now in this way, the electrons, whenever it happens to receive the electron from the metal, electron rich metal, the electron goes into the pi star orbital. So once it goes to the pi star electrons, a pi star orbital, so the bond order which should automatically, so this, after this is a sigma donation from the carbon monoxide to metal, okay. That is how the initial bond is, and then this is a, call it as a pi back donation from metal d orbital to the carbon monoxide pi star orbital. So the bond order is equal to number of bonding electron minus anti-bonding electron by 2. So now as the electrons from the metal is donated back to the pi star orbital, which is the anti-bonding orbital of the carbon monoxide, so in that case what will happen, bond order should decrease, because the electrons are pumped into the anti-bonding orbital. So therefore the bond order of carbon monoxide in metal carbonyl should decrease. So that's why if you see the metal carbon, so this bond order is not anymore 3, it will be less than 3 depending on the metal, how much electrons is donating, and then in that case this bond also will be more than 1, because not only sigma bond donation but the pi back donation also is happening here. So that bond order here also will increase a bit, and their carbon monoxide bond order will also decrease, and this depends on the how electron rich is the metal. If the metal is very electron rich, it will donate much more electron, so than as compared to the metal which is a less electron rich if it is a oxidized species. Okay. So this can be, as you know, that this can be easily understood based on the how we can find out whether this bond is weakened or it's like nothing is happening to that. Bond strength, how do you calculate? What is the experimental you do it? IR stretching frequency, no? That is very easy to do it for the metal carbonyl, and I think you have seen also the IR machine here. So in that case, if you have a free carbonyl, free carbon monoxide, the IR stretching frequency comes around 2143 centimeter inverse. Now as soon as it binds to the metal carbon bond becomes stronger, but the carbon oxygen bonds become weaker because the electrons are donated back into the pi star orbital. So if this is the case, carbon oxygen bond strength decreases, then what will be the case of the carbonyl stretching frequency? Will it decrease or increase? Because this stretching frequency depends on the bond strength. As the bond is stronger, the stretching frequency will be more. If the bond is weaker, stretching frequency will be less. So in that case, as the bond order here is less than 3, it is in between 2 and 3, mostly 2.5. So in that case, obviously the stretching frequency should decrease from here. So now not anymore 2143 centimeter inverse. If you have a metal carbonyl, metal carbon carbonyl complex compounds, so in this cases bond strength will decrease and accordingly stretching frequency will decrease, and that is the range of 2120 to 1850 centimeter inverse. Now if you have a bimetallic system where you have something like that, the metal is the carbonyl is connected to two metals. So in that case, the back donation from two metals will impact the carbon monoxide bonding. Pi back donation, what we are talking about, two metals they are connected, so the pi back donation will be more. So this carbon and oxygen bond strength will decrease further, and you will have a, if it is a new bridging CO, we call it as a bridging CO, right. So it is bridging between the two metals, so it is a bridging CO. If you have a bridging CO, will be further decreased, and then accordingly the stretching frequency is proportional to the bond strength. As the bond strength increases, the stretching frequency increases. As the bond strength decreases, stretching frequency decreases. So in case of bridging carbonyl, which is bridging between two metals, the bond strength further decreases and you will have a stretching frequency further less, and you will have a 1700 to 1815 centimeter inverse. Alright. So this we talked about the carbonyl. Now if you talk about the metal system, the metal will also affect, right. So if you have, if you have a metal which is, let us take some, so if you have a metal which in plus oxidation state, which is a metal which is zero oxidation state, which is metal which is minus oxidation state. Okay. So in that case, overall you should have that the same number of electron. It has to be, first it has to be isoelectronic. If it is not isoelectronic, then it is not a reasonable way to compare. Okay. First it has to have the same number of electron. If it is a less number of electron, you cannot compare. So overall, first they have to have a same number of electron. Okay. So, whatever it is, let us say we will consider total as a 6 electron, okay, total 6 electron, like chromium is a total 6 electron. Now, if you go for chromium to manganese or below vanadium, then you will have a vanadium should have been the -1 and then manganese has to be +1, right. If you just simply take is manganese 1, what is the electron? 7 minus 1 is 6. So, if you take it as a chromium which is a 6 electron, and then cases what you have to take vanadium 5 plus 1, that will be 6. So, overall you will be having the same, this is an imaginary I am telling. So, in that case 6 electron. Now, if you have the corresponding carbonyl compound, in which cases you will see the lowest stretching frequency. So, given that every metals or metal ions have the same number of electrons, 6 electrons. Now, we are considering the corresponding carbonyl complexes which is MCO6 N plus, okay, N could be 0, +1, -1, whatever it is, okay. Now, in that case Z, which one will have a maximum carbonyl stretching frequency? Because one case is a +1, one case is 0, one is -1. No, +1, because +1 is it's already +1 charge. It will not be willing to donate much electron because it's an oxidized species +1. But in that case, metal 0 will be better than this because it doesn't have any negative charge, but it is still better than 0 because it's a neutral species. But when you go for M-1, because of the negative charge, it will have a much more electron density to be donated to the carbon monoxide. So, in that case M-1 will donate much more electron density to the carbonyl. If it donates more, then the carbonyl stretching frequency will reduce further. So, just to give you the data here, so manganese CO6 plus, so the stretching frequency of new CO we are talking about 2090 centimeter inverse. Now, if you see that chromium CO6, that value correspond to 2000, and if you take the vanadium CO6 minus, that value goes to 1860 centimeter inverse. You clearly see that as the metal in plus oxidation state, it is the higher new carbonyl stretching frequency. As it goes from the +1 to 0 to negative species, charge species, then in that case stretching frequency reduce drastically. So, you can use the same concept based on not only the metal oxidation state, depending on the different ligand what we have around, that also will decide how it changes the carbonyl, because as the metal become electron rich, this is one of the way to consider the charge of the metal ion, but also it depends what are the ligands around it. If you have a very electron donating ligand, we will take one example. When you are talking about the phosphine, that will be very good donor to the metal. Metal will be more electron rich, then the carbon monoxide stretching frequency should decrease further, okay. So, now in the same way, when you are going for a, is fine now, okay. If you have any difficulty, please ask, okay. Now, in the same way, when you think about the metal alkene complex, this is looking like this, perpendicular plane of the metal, this is like a plane, and this alkene is perpendicular to the plane. If you think this is a plane and this alkene is like that, okay. Now, this is a binder, okay. Now, in that case, the bonding scenario is almost the same as of carbonyl, okay. So, if you look at this bonding here, the alkene is, you have a pi bonding which is plus and minus, okay, and then you have a pi star because it is a double bond. So, pi bond is there, pi star is there. So, it is a plus minus This is the overall of alkene. This is a plus and minus, and this cases is anti-bonding. This is a pi star and this is a pi bond, right. Now, if you have a metal, the same way you can consider metal which will have that. So, it will be face to face overlap between this alkene pi electron and as well as it will have, right. So, again it will be back donated and this will be forward donation from the alkene to the metal and from there to there, okay. So, overall if you look at this bonding here, so if you simply think about the alkene here, this is hydrogen. What is the bond angle here? This is alkene, 180. 180 happens to what? If it is a linear molecule. No, that is for tetrahedral. 1 or 2. This is an sp2 hybridized. What is the angle? 120. After so many trials we got it. So, this is 120 degree, and are this all this hydrogen is in the plane or not plane? Huh? Huh? Alkene is a planar molecule or not? Yes. So, they are all in plane. This all this alkene, all the hydrogens in plane, and the bond angle is 120. If it is an just a free alkene. Now, after bonding to the metal, the scenario changes a little bit. In case of carbon monoxide, what we discussed, that after bonding to metal, carbon oxygen bond strength decreases, and accordingly we have seen that it will be reflected in the corresponding carbonyl stressing frequency. In turn, it gives you the idea about the bond strength. Now, if you see that here is alkene, the same scenario is happening. This pi electron is donated to the metal, and this d pi electron is donated back to the pi star orbital of the alkene. So, if it is donated back to the back donation happens to the pi star orbital of alkene, then what will happen? The bond strength should decrease or increase? Simple, no? Because it is donated back to the pi star orbital. So, therefore, the bond strength should decrease. If the bond strength should decrease, means the bond order also should decrease. Bond order should also decrease. Now, if it is a free alkene, the bond order is 2, but once it binds to the metal, so let us say this is a Giese salt which is a structurally characterized salt. In that case, the bond order cannot be 2, it has to be less than 2. Now, if it happens that it is less than 2, what are the structural features you expect to see here? Because it is not anymore the double bond, and not anymore you will not see that all in plane, because if it is a purely alkene, then it will be all the proton or whatever is in plane, and the bond angle will be 120. Now, if it just because of this pi back donation, bond order decreases. It is not anymore is sp2 carbon here, but it will shift towards slowly. Single bond means what will be the hybridization then? sp3. sp3 cases bond angle is what? 199. Okay. So, if it is a sp2, then it is 120, but because of this bonding, it is not anymore a double bond. The bond order decreases, it moves towards the single bond. So, it is not a single bond, but in between a double bond and single bond. So, therefore, this alkene, all the substituent will not be in plane, because it has to go from 120 to 109 in between. So, this substituent will be slightly bent. So, more bent like this, all this hydrogen is not exactly like that, but it will be because of the bond order decreases, it will be slightly bent, and as well as the bond length should increase. Bond length, not the bond strength. Bond strength, if it is stronger, then the bond length will be shorter. If it is weaker, the bond length will be increasing. So, if you see that ethylene cases, bond order of carbon-carbon bond length is about 1.3 angstrom, 3-4 angstrom. But in that case, if it is in the coordinated alkene, the bond order goes to 1.37 angstrom. You clearly see that after binding to the metal, bond strength decreases, so the bond order increases, and that's what it reflects. And as well as if you have that, if you look at the planarity, it's also slightly deviated, the substituent will be little bit bent from the substituent. In the similar direction, instead of, see, if we compare the three molecule, let us say ethylene versus so nitrile, or you can also think about the fluorine containing compound. So, between these two, which one you feel like will have a longer bond length? Seems to have a longer bond length. Why? You have to think the pi acceptance capability of the alkene, because that is how the metal electrons are donated back. So, if it is a better acceptor, it will accept much more electron from the metal as compared to the cases where it is not that good. So, you have a hydrogen, right, but here is the nitrile group, C triple bond N, nitrile here. So, if it is there, so it will be pulling much more electron towards it. So, if it is pulling much more electrons towards it, in that case the bond order should decrease further as compared to the ethylene what we discussed. If you have a substituent which will help the alkene, the pi star orbital, to pull more electron, then it will be the bond order should decrease further, bond strength should decrease further, so bond length should increase. And if the bond strength, bond length increases, it is slowly approaching towards the single bond. So, this nitrile group also will be bent from the alkene plane. Okay. So, that is how we can understand that how the bonding, if you know the bonding, then you can easily find out what will be the implication of that bonding towards the towards the structural features of that particular complexes. Okay. Now, let us move to the other ligand system what we discussed. This is a very classical examples of organometallic chemistry ligand system. So, the next one is the PR3 phosphine. It is like a NH3. NH3 is also, it has a one lone pair and it also has one lone pair, right. Okay. So, what is the structure of that? How it? This is a safe, actual safe, trigonal pyramidal. So, it is a all the substitution in the plane and you have a phosphorus on that and then you have a lone pair, right. So, now this is also very important class of ligand in organometallic chemistry. Again going back to that, right, Wilkinson catalyst. It is a very well established ligand system. Now, if you see that there is specifically they have used a phosphine with a phenyl group. Now, what will happen if I change that PME3, will it act as a catalyst or will not? If not, why? It is very simple changes, right. So, you have that rhodium PPH3, PME3, will it have any changes or not? What changes will have? No, first of all, will it act as a catalyst? If it acts as a catalyst, will it be better than this? No idea. Okay. First of all, it will not act as a good catalyst. That's why they have used specifically phosphine with the phenyl substrate, not with the methyl substrate. Okay? Huh? That's what we are going to learn. Okay? So, now the question is that in order to understand that why it is not a catalyst and why they have used the phosphine with the phenyl substrate. In order to understand that, you have to find out the electronic property of phosphine as well as the steric properties. Okay. So, both electronic and sterics play a major role in the catalytic activity of any metal catalyst. Okay. So, first have you heard about this name Tolman? No. Okay. So, Tolman electronic parameters, which is known as a commonly Tolman TEP. Okay. And also he developed one method for the steric, and that is known as a cone angle. Theta. We will see that how it's help us to understand the structure, property and activity of metal complexes. Now, if you first start with this cone angle, which gives us a idea of the steric property of the complexes. So, what he was doing, he was trying to, he is from DuPont Chemical. Have you heard about that name? It's an industry. Okay. So, he was working on the nickel L4 catalyzed hydrocyanation of 1,3-butadiene with the HCN, and you get the corresponding this compound. Okay. And what he realized, hydrocyanation means add the hydrogen and nitrile here, and that's what he was doing. Now, what he realized that depending on the L, which is basically a phosphine ligand system, and what he realized that the dissociation of L is very important. So, to understand that which ligand will dissociate further, and that is what you can calculate the KD. There is a standard method which is the dissociation constant of that, and that is very critical to understand the activity of this particular complexes in the hydrocyanation reaction of this. So, what he did, he just made a list of range of compound and calculated their KD, and accordingly he could find out some of the activity trend. Now, what he has proposed that if you consider the nickel and phosphine, any metal phosphine, let us say it is a metal, nickel cases the distance is fixed. So, metal and you have a phosphine here. Phosphine means it is a trigonal planar pyramidal. So, you have this is like a lone pair which is donated to the metal, and you have 1, 2 and 3. Right. So, what he has developed, so this is a any R group, I am not talking about that which particular R group, any R group can happen. Okay. So, in that case what he has developed, you just make a cone in that, and that cone basically this is the cone. So, outermost atom of this all this substrate you can build up, and then it will form a cone at the metal, and this is a acute angle which is known as a theta, which is coined name as a theta, which is a cone angle, and that gives you an idea about the steric bulkness of the phosphine, because if a smaller phosphine, your cone here whatever is generating, and accordingly cone angle will be low, but if it is a very big, then your cone angle increases accordingly. If it is a increase, it is like a simple like this. So, if it is smaller phosphine, it will be like that. If it is a little bigger phosphine, it will go just like that. Okay. So, based on that simple idea and the metal phosphine bond distance for the nickel, it was 2.28 angstrom, but in general any metal it is about 2.12 to 2.55 angstrom is Harris. So, this is overall phosphine system, and based on this nickel system only he has given a table to understand the steric properties of this all this phosphine based phosphine. So, you can easily find out that how sterically bulky is that phosphine. Okay. So, I will just write some of the values here. So, if for example, if you take the phosphine pH3, we are talking about the theta versus pF3 . So, you can see that systematically how it is changing. pH3 means you have only hydrogen attached to phosphorus. It is a very small phosphine ligand. So, it can easily find out that it is the cone angle is the smallest one. Now, as you keep on changing, as the substituent on the phosphorus becomes bigger here, so the cone angle also accordingly increases. So, there is a standard table in that any book you will find out that as the phosphine becomes bigger, then you will see that it is the theta angle is increasing. So, accordingly you can find out which phosphine is good for you, because if you are very bulky you cannot put when it is binding to the metal it cannot bind, because in that case sterically it will be very much problem to be attached to the metal. It is very big means you cannot put much more ligand system around it. So, that gives an idea about the sterics of this. So, you do not have to go and calculate, this is the method and it is calculated, it is available in a table, that is it, as simple as that. So, that gives an idea about the sterics of the system. Now, how it will be affecting the electronic property. Electronic properties, how to find it out. So, this is a Tolman electron parameter. And again that whatever the concept we have built up, this is the carbonyl stretching frequency, we can use that and that is what it will have, we will use it here. So, if you take the nickel tetracarbonyl and react with some of the phosphine and it generates the corresponding nickel CO3 PR3. Now, if you get that compound, you can synthesize this, no problem at all. Then you have the nickel carbonyl phosphine species, right. Now, if you simply make that compound, go for higher stretching frequency, then you will find out the what? The new CO of particular carbonyl, right. So, now with this particular carbonyl cases, carbonyl stretching frequency, how it is decreasing based on the phosphine, then you can find out the donor strength of the phosphine. Because if you have here phosphine which will be donating more electron to the metal, then metal will be more electron rich, and if the metal is more electron rich, that will in principle donate back electron to the carbonyl, and if the carbonyl stretching frequency should decrease, right. So, if you have a phosphine PR3 whose donor strength increases, then the new carbonyl should decrease, as simple as that. So, it should decrease. So, it gives a nice probe, right. So, if you just make this compound, it gives a nice probe, then you can just simply measure the corresponding carbonyl stretching frequency and you can find out the donor strength of the phosphine. Now, if it is a very strong donor, you will have a very weak carbonyl stretching frequency. If it is a weaker donor, you will have a more carbonyl stretching frequency. Now, we use a term called chi, which is the stretching frequency of new carbonyl stretching frequency, which is corresponding to the P tertiary butyl 3. So, when the phosphine is p tertiary butyl, this is the considered to be the strongest donor, strongest sigma donor, and that is what he is fixing that as a new any other phosphine, whatever you wanted to probe, this one minus this one. So, this is the chi value. So, it shows that this is a reference, just to show that it is a reference. So, if the carbonyl stretching frequency is more, right, then in that case the phosphine is weaker donor. So, as the chi value is increasing, because this is a standard, this is like a reference, okay, it is fixed here. So, in that case whatever the carbonyl frequency, if it increases, chi value should increase. If the carbonyl stretching frequency is increasing, means this is a weaker donor. If the carbonyl stretching frequency decreases, so then means it is a stronger donor, accordingly chi value should decrease. So, overall what we see that chi value increases means it is a weaker sigma donor, and chi value decreases is a stronger sigma donor. Let us have some data. This is also already table, you have a standard table that you can easily use it. Let us see that p tertiary butyl 3 phosphine, the complex we are talking about nickel CO3 PR3, this is the complex we are talking about, and you are talking about the new CO of the particular phosphine, and this is the chi value. So, for the phosphorus tertiary butyl phosphine, which is considered to be the strongest phosphine donor, okay. So, in that case is the value goes to 2056.1, this is in centimeter inverse, and the chi value obviously should be 0 because we are considering with respect to the tertiary butyl phosphine. So, this case is 0. Now, if you keep on moving to the other system, cyclohexyl, you know what is cyclohexane, right? Yes. So, cyclohexyl cases, it is the almost the same, and it is only 0.3. Now, if you go for the other cases, for example, p ethyl phosphine, in that case we are getting 2061.7, and then accordingly it will increase to 5.6. Now, if you compare that, or PME3, it will be, we need to know that 2064.1, 8.0, and PPH3, if you see here 2012.8. Now, what we see here that between these two PME3 and phenylphosphine, which one is a stronger donor? Because in case of phosphine, which is trimethyl phosphine, that you are seeing that this is carbon stretching is lower as compared to the triphenyl phosphine. So, definitely trimethyl phosphine is a stronger sigma donor as compared to the PPH3. Now, based on this understanding, we have the corresponding steric property, which is based on the Tolman-Cole angle, and here is the electronic property, which is known as a Tolman electron parameter. We have an idea about the steric and electronic properties of the phosphine. Now, if you go back to the catalyst and see rhodium, now can you tell me that why one cases you may not, I mean one case is the trimethyl phosphine cases, this cannot act as a good catalyst, why they have chosen triphenyl phosphine? You think? No idea. The data is given, complexes are given, only thing is that you have to correlate. As I already told you that this is Wilkinson catalyst cases, that the reaction proceed via dissociation of phosphine. This is one of the important step in Wilkinson hydrogenation reaction. One of the phosphine gets dissociated from the metal, right. So, in that case also you are looking for dissociation of phosphine. That much clue I have given. Now, you tell me that why that one case is better, one case is not good. That is the whole point. Okay, triphenyl phosphine, you see that is a weaker donor based on the chi value and the carbonyl stretching frequency as compared to the phosphine. The bond between the trimethyl phosphine and the rhodium, this bond we are talking about versus this bond is stronger as compared to this. So, dissociating the phosphine from the metal will be difficult, one case. Second case, if you see about the steric also, the phosphine, triphenyl phosphine, the steric bulk is huge, 140, and in that case is 145 and this is 118. So, sterically also, that whenever you are thinking about the any reaction, sterics also play a major role. If you have a bulky ligand around it, that will easily push the ligand out when this is sterically bulky. So, triphenyl phosphine that respect also bulky as compared to the PMA3. That is how you try to, you correlate the activity with their the structures, alright. Now, the one more questions, if you see that nickel CO4 versus nickel CO3, any phosphine versus nickel CO2 PR2 whole 2. So, in that case, so these are the three different compounds you are given, nickel CO4, nickel CO3 PR3, nickel CO2 PR3 whole 2. You don't have to consider the whatever the R group, the same R group, okay. So, now here which way the carbonyl stretching frequency will change? Hmm? Hmm? Okay, you try later, okay. Okay. So, there are several factors you have to consider, because it's 4 carbonyl versus 3 carbonyl versus 2 carbonyl, okay. Okay, now this is you know what is that catalyst? Have you seen anywhere? Huh? Huh? What catalyst is that? Have you heard? I told you, no, Gruff's catalyst, metathesis reaction, who got Nobel Prize. Yes. So, this is, that is the, now this is not a Gruff catalyst, okay, you have to substitute it. So, is it possible to substitute this phosphine with the cyclohexyl phosphine? Because when you plan a reaction, then you have to have an understanding whether it will go or not. So, now you have a phosphine complex, because this precursor is easy to make, ruthenium PPH3 whole 3 Cl2, readily we can make it, and you can make the corresponding complex. Now, if you want to have your desired complexes, you have to do some of the modification. So, one of the cases is triphenyl phosphine is substituted by PCA3 or any other phosphine. Will it happen here or not? The question. You have an idea about the phosphine donor strength. So, between the PCY3 and PPH3, which one is better? PPH3 is stronger? No. Weaker donor as compared to the cyclohexyl, because PPH3 is the aryl phosphine, whereas PCY3, which is a aliphatic phosphine, right, because this is cyclohexyl. So, in that case, PCY3 is a better donor as compared to the aryl phosphine, and you can easily generate the corresponding the Grubbs catalyst, which is the first generation catalyst. So, here you can easily make the corresponding this is ruthenium. So, this is a Grubbs first generation catalyst. But it is not a good catalyst. Okay. So, he modified it later and he added one basically it is a acetyl, then you have ruthenium here, he modified through this catalyst, okay, and this is known as a second generation catalyst, and this is a very active catalyst. Okay. So, this is, so you have now we will move it from phosphine to carbene, and this is known as an N-heterocyclic carbene, and this is a very active catalyst as compared to 2-PCY3. It is one of the PCY3 substituted by carbene, and you are getting this catalyst, which is a second generation catalyst, and that is how people are slowly moving to carbene. Okay.
SwayamPrabha, Digital India, Educated India.